Hey, it's Mr. Allred, and we're going to introduce a new function. It's called the logarithm. But before we get there, let's talk about y briefly. So we're going to talk about exponential functions, which is where we've been. And in the middle of the page here, I've got an exponential equation. 35 equals 4 raised to the x. And in trying to figure out what x would be up to this point, the only way we have is to kind of guess numbers and plug them in. Use our calculator. 4 squared is 16. 4 cubed is 64. So in theory, the x should be between 2 and 3. And then we have the opportunity to go to our calculator and do 2.1, 2.2, and if we find that, then we could keep going out more and more decimal places. But that method just makes it a guessing game. So we're right now limited in the way that we could solve exponential functions. So it would be nice if we could get that x there, the thing that we're trying to solve for, out by itself. And that's what the the logarithmic function is going to do. So here in the top is the definition of the logarithmic function. Okay? And it's a definition, so you can ask a lot of questions about it, but there is no explanation outside of this is how we've defined this function. Now, once you accept the definition, you can follow it up with many rules that make sense based off of that definition. But it's really just a different way of writing an exponential equation or an exponential function. So if we had the exponential equation or function, x equals a to the y, exponential because there's a y up here in the exponent position. So again, x equals a to the y. We're going to say that's equivalent, a little rearranging, to the function or equation y equals, so that gets the exponent by itself, log, who knows why we have this name, but log base a of x. So these x, a, and y are placeholders, and we're going to use them in a moment. But keep in mind and look at what we've got here. The y was the exponent. That's the part that gets to be by itself. Now it doesn't have to be y, but it has to be that placeholder. The exponent ends up on the side by itself. The base of the exponential is the base of the logarithm, and the result from the exponential is the input of the logarithm. So the part that was easy to get to in the exponential, the x over here, is hard to get to in the logarithm. The part that was hard to get to in the exponential, the y, the exponent, is easy to get to in the logarithm. But let's just identify these placeholders. So let's use some colors here. We've got x, we've got y for our exponent, and we've got a for our base. So we're going to take some exponential expressions down here and rewrite them as logs. So let's look for the parts. The first one we have is 125 equals 5 cubed. Well, the first thing we need by itself is an exponent, which will be 3. So it'll go right here. And we'll have a base of 5 that I'll write down here. And we'll have an argument of 125. So let's come over here. We will have 3 equals log base 5 of 125. And all I'm trying to do right now is get you comfortable with rewriting between the forms. Sometimes we'll have an exponential form that will be beneficial to write in log form. Sometimes we'll have a log form that will be beneficial to write in exponential. But the next one we have is 21 equal to 7, which is the base, to the c, which is the exponent, but will end up by itself on the other side. So c equals log base 7 of 21. And I'm not trying to figure out what c is right now. And I'm not picking up a calculator. The next one is not in the same order. So depending on how I want to tackle that, the base here is w to the 6 equals 42. So w is the base. The 6 is the exponent. And the 42 is, what color I need? Is the argument. Okay, so I'm going to write it out as 6 equals log base w of 42. So hopefully you can see the transition from one side to the other. Okay. Now I have more examples, but in these we're going to go from the log form over to the exponential. So let me see if I can keep the same colors I had before. So before I had the exponent in purple, I had the argument in green, and I had the base in blue. So the first log we have here is 5, which is going to be an exponent, equals log base 2 of 32. And I certainly don't expect you to do all this coloring on your paper, but that'll turn into 32 equals 2 to the 5th. I sure want to make sure you understand what's happening right now. 32 equals 2 to the 5th. And that's actually a true statement, since there's no variables in there. All right, next we have r equals log base 4 of 2x plus 4. So these are just placeholders, so there can be some scary looking stuff in there. So that's going to be 2x plus 4 equals 4 raised to the r. The last one is written a little bit backwards, but we've got log base m of 39 equals 90. Purple. So let's fill that in. We can have 39 equals m to the 90. So you're always looking at the place that it's at, not necessarily the value, because we could call different things x, we could call different things y, we could have different parts, and we could be missing various parts at different times. So just getting back and forth between the two is going to be helpful. So in different situations, it'll be beneficial to get the log form. Other situations, it'll be beneficial to get the exponential. So there's a couple different ways logs can be written, or at least with a couple different bases. The one we've seen that uses a base a, what was I using on the base? The base a is just our regular run-of-the-mill definition of a log. But there is some logarithm bases that are frequently used, so they get their own special notation. So if we have a exponential that has base 10, generally when we write it in log form, we don't even write the base with it. This is kind of like when we do the square root and we don't put the little index outside of 2, because square root is so common that that's the one that we expect it to be. But if it's not a square root, then we'll put an index out there like a cube root. We'll put a little 3. So this common log, base 10, similar to what the metric system is based off of, similar to scientific notation calculations, is very frequently used. But x equals 10 to the y, usually we would write that as y equals log of x and just not even write a base. The other one that's frequently used is base e. This is commonly used in finance and biology. We've seen examples with compound interest where we have the continuous form. But if we have base e, usually we don't write that either, but we denote it as ln instead of log for the natural log. So if you ever see ln it automatically means base e. So x equals e to the y would be written as y equals ln of x, and we just call that ln the natural log. I'm not sure why it sounds backwards. You would think NL maybe, but maybe it just looks better. There might be another reason for it. But if you ever hear me say natural log, I'm talking about base e. If I say common log or base 10, you should know that. But most of our logs, if they're not one of those two, we will have to write a base. And some of the benefits of the other two forms, the common log and the natural log, is that almost all of your calculators will be able to do these, while most calculators can't do just any base. I think it really takes a toll on calculators to do logarithms the way it's formatted, so they can't do just any of them, most of them. Alright, so let's just do a couple examples rewriting these. So here I've got the exponential d equals 10 to the 8th. Now we could write that using just the regular old definition of a log, but if we want to, we can kind of convert it over to log. We don't have to write the 10 of d equals 8. And if we wanted to put the 10 there, it wouldn't be wrong, but there's no need to. So log d equals 8. The next one, we're starting with a log, so we got log of 40 equals q. So it's understood that there's a 10 down here, so when we rewrite it, the base is 10, it's to the q, and that would give us 40. If we need to go back to the color system, we know that the outputs are the arguments of the log. We'd know that the exponents end up on the side by themselves. And we would know that the bases, at least in these cases, didn't have to be written. They were understood to be base 10. Okay, in the other forms, the natural log that we're going to work with, e to the 12 equals p, so the base is e. The exponent is 12, and the argument is here, or the result would be p. So I don't even have to write that base, so I'll use natural log of p equals 12. Okay, so natural log of p equals 12, but I don't need to write that e down there. And the last example here, we're starting with a log form and we're going to an exponential. It says natural log of 7 equals h. So the argument here is 7. The exponent is the h. Ooh, I wrote that backwards, didn't I? No, I didn't. And it's understood that the base here is e. So that would look like e to the h equals 7. So just got to get used to the three forms. If you have the definition of the log, that is usually enough. And when you don't see a base, it's either one of two things. It's either log or it's either 10 or it's either e. All right. Thank you.